So far we have described gravitational waves, small gravitational waves, which are linear solutions of the linearized approximation to the Einstein equations. And now, in the remaining part of the lecture, we're going to discuss exact solutions of the Einstein equations that are describing some kind of gravitational shock waves. But our discussion will be not very detailed, more concise in this respect. The lacunes in our arguments are, remain as exercises for the readers. So, consider Schwarzschild metric. So the Schwarzschild metric, as you remember, is as follows. 1 minus rg over r dt squared minus dr squared 1 minus rg over r minus d r squared d omega squared. And let us make the following coordinate transformation in this metric. R equal 1 plus rg over 4 rho squared times rho. If one makes this transformation, to do it remains as a home exercise for those who listen to these lectures. One obtains the following metric. The result of the coordinate transformation is just 1 minus rg over 4 rho divided 1 minus rg over 4 rho plus squared dt squared minus 1 plus rg over 4 rho to the fourth times d rho squared plus rho squared d omega squared. Okay, so why did we make this transformation? Because the obtained metric is up to this conformal factor is flat. Spatial part of it is flat. So this metric is flat, and we can make the following coordinate transformation. If we represent rho squared as x squared plus y squared plus z squared, so we can make in spatial part of this metric to the Cartesian coordinate, transformation to the Cartesian coordinate. So we can make the following change such that this d rho squared plus rho squared times d omega squared is equal to dx squared plus dy squared plus dz squared. Now, once we made this transformation, we have the following situation. We can make a Lorentzian boost along the z direction. Lorentzian boost along the z direction. So make the following transformation. That t bar is gamma t plus gamma v z, and z bar is equal to gamma v t plus gamma z, where gamma is just 1 square root of 1 minus v squared. The result of the transformation, of course, the metric is not Minkowskian, hence this transformation is not an isometry of this metric, and as a result, the metric will change somehow. How it remains as an exercise for those who listen to these lectures. Well, it's not hard to see how it transforms, but then we want to make the following limit. We want to take the following limit. So we want to take gamma to infinity. So v to 1. So take the velocity to the speed of light. Yeah, the result of this transformation is, of course, black hole which moves with velocity v. So this was a black hole at rest. After this transformation, we obtain black hole which moves along the direction with v, velocity v. Now we want to take this black hole moving with the speed of light. So we take this limit such that the mass of the black hole goes to 0, but Rg times gamma over 2 is fixed constant. So we take gamma to infinity, Rg to 0, but we keep this quantity fixed. This quantity we call as Rg times gamma over 2 is kappa times p, where p is the momentum, modulus of the momentum in this approximation, in this limit. What we obtain? We obtain a light-like wave. As a result of taking of this limit should be light-like particle, light-like source, moving with the speed of light with momentum p, finite momentum p. This is kept fixed. So the result after this transformation and taking this limit, this metric is transformed in the leading limit, is transformed to the following expression. It's du dv plus 2h. H is a function of u and x perpendicular. What is x perpendicular I will explain right now. Minus dx perpendicular squared. So this is the resulting metric of after taking this limit. So let me explain the notations. X perpendicular vector is just x and y. So this is just dx squared plus dy squared. Then u is just t minus z over square root of 2, and v is t plus z over square root of 2. And h of u and x perpendicular is just the following function. It's kappa times p, this kappa and p, kappa is Newton's constant, times delta function of u times log modulus of x perpendicular. So that's what we obtain taking this limit. The other way to see that this metric is a solution of GR equations of motion is to use this ansatz for the metric and calculate that the only non-zero component of the Riemann tensor, of Ricci tensor, the only non-zero component of the Ricci tensor of this, for this metric is just Laplacian along x perpendicular, acting on h as a function of u, x perpendicular, where, well, Laplacian perpendicular, x perpendicular, is just dx squared plus dy squared. So Laplacian in the perpendicular directions to the direction of motion of this body. So, using the fact that Laplacian of x perpendicular of log x perpendicular is actually 2 pi times delta, two-dimensional delta function of x perpendicular. So basically log is a two-dimensional green function. Using this fact in here, we obtain that this metric solves Einstein equations with the following source. TUU is just p times delta of u times delta two-dimensional of x perpendicular. So this is the other way to see that the obtained metric solves Einstein equation. This solution is called Penrose parallel plane wave, or PP wave. PP wave. It describes so-called shock wave, whose world line is, according to this, is described by equation u0 and x perpendicular equals to 0. So the world line of this guy is u equals to 0, x equals to 0, where the source is. It travels with the speed of light, because this equation just tells us that the wave travels with the speed of light. So the momentum of this wave is given by p, according to this expression. And this metric is defined beyond this point, beyond the point where the source is, because the source, where the source is, we have a singularity. Beyond this point, this metric is defined, and it is not asymptotically flat, according to this expression, and it has a naked singularity, as one can see. Now we're going to describe properties of this metric.